To understand how you apply the Rhize manufacturing ontology, you first need to have a comprehensive understanding of the requirements of your use cases. What does the business require of the operations domain for purposes of achieving its singular goal of being profitable? Let's go back to our EBR use case and understand how we can go about mapping those requirements onto the ontology. All of manufacturing is made up of resources and processes. That's it. It may seem a bit strange that there are only 3 resource models, but consider it for just a moment. Every physical object in a manufacturing plant fits into either equipment, personnel, or materials if it's relevant to your operations. There are 3 resource models described by this ontology. The first is equipment, which is the model that everybody seems to have some understanding of. Enterprise, site, area, line, work cell. Unfortunately, that's where most people get stuck, because they view the rest of the system components as belonging to the equipment. They don't belong there, and attempting to model your ontology in that way is very likely to end in at least a partial failure of your digital transformation program. Your equipment is an operational resource, just like personnel and materials are resources. It tends to get all the focus, especially at the OT layer, because most time series data originates with the equipment, but equipment is just one part of the operations puzzle. In the Rhize manufacturing ontology, the equipment model comes directly from ISA 95 and is simple but quite powerful. Equipment and its properties should be modeled as classes. Equipment can be made up of other equipment, and properties can contain other properties. So, a manufacturing line can be modeled as an equipment class, and the work cells that make up the line can also be classes. An equipment class has properties which may contain other properties. It's a very simple model that is enormously powerful and allows us to build very complex systems in a standard way. How deeply nested your equipment model is will be a function of the needs of your business, not a function of your MQTT topic structure. A piece of equipment will very likely go through iterations of detail as successive use cases define more properties and relationships. Not every use case needs every piece of detail, nor does it need every piece of equipment. Some use cases, like material genealogy, don't even require an equipment model. Regardless of what decisions are made in determining how you model equipment, you can see from the image that each of the components of the Rhize manufacturing ontology is an entity with a set of relationships. The second resource model is personnel, and its ontological model looks a lot like the equipment model. People are a resource to operations just like equipment. There are classes of people: supervisors, engineers, operators, and many others. Personnel have properties. There are obvious ones that come from human resource systems, things like start date and wage, but operations usually isn't concerned with those properties. What matters to operations is what shift the operator works on, or what class of equipment an engineer is trained to troubleshoot. The third resource model is the material model. A material can be a raw material, an intermediate material, or a finished good. It can be made up of lots and sublots. A material can be composed of multiple materials. It can get complex, but at its core, it's still a relatively simple model made up of material definitions and their properties. And if you stay guided by the ontology, instead of trying to reinvent the wheel, it all comes together in a very predictable way. The final part of the ontology is the process model. This is where things can get hard, but getting this part right is fundamental to the success of your digital transformation. Not every process requires all the resources models, but everything related to manufacturing operations has a process, and in most off-the-shelf MES products, this is where the data model fails. Understanding how to model your process to the Rhize manufacturing ontology mandates that you know what the business requires from each use case. What are the events that drive the flow of operations? What are the inputs and the outputs to those events? How do the operators interact with the process, both physically and through software? And there are many other questions whose answers come through the process of requirements gathering. Part of the difficulty comes from the fact that ISA 95 and the Rhize manufacturing ontology provide multiple ways to model your process, and you can achieve the same outcome from multiple paths. Understanding which model to use comes down to understanding the process at a very deep level. Is the process static? Is a particular product always made with the same equipment, using the same resources by the same group of people? Is the control of the process hard-coded into the DCS, or is it managed by a batch control system? Is the process dynamic? Is it defined in an MES, or is it driven from the ERP? Which road you go down will be defined by those questions and many, many others. If you have a largely static process, you might use the process segment model. If you have a highly dynamic process, you may use operations definitions or the work model. The modeling process is when most digital transformation programs fall over for one or two reasons. One, the commercial off-the-shelf MES solution being used wasn't meant to be customized, or two, the company decided that it could be built from scratch, but without an ontology, ended up with an unsupportable set of architectures, databases, and applications. Mapping your system to the Rhize manufacturing ontology and modeling for resources and processes is hard, but it's much easier when you're guided by a framework. The adage that we use here at Rhize is that if you think ISA 95 and the Rhize manufacturing ontology are hard, then try getting to a complete operational model without it. Data quality refers to the condition of data that makes it fit for its intended uses in operations and decision-making. High-quality data is considered accurate, complete, consistent, and timely. Essentially, it's data that can be trusted and relied upon to provide meaningful insights and support effective actions. For as long as manufacturing companies have been collecting data, whether that was on paper, or manual entry to spreadsheets, or automated collection, there have always been issues related to data quality. If you have legacy systems like data silos and a large number of APIs that tie it all together, you may think that getting your data into an accurate, complete, consistent, and timely state is impossible. It isn't. The solution to the data quality issue is straightforward. Ensure that the Rhize manufacturing ontology is in the nexus of all of your operational data and systems. All data entering the hub is transformed to comply with the language of the ontology so that the data will be accurate because it has been transformed to comply with the standard. It will be complete because the data is stored according to the ontological definition of each entity, even if the entity's data originates across multiple disparate systems. It will be consistent because the ontology is finite and used by all systems as the source of truth, and it will be timely because the data hub is an event-driven, real-time, low-latency platform. In the next video, we're going to look at the challenges presented by legacy applications and show you how an ontological approach allows you to strangle them out one at a time.